Okay, so I guess most people are already here, so we can start. So this last lecture in a series of 4 lectures will be very different from the 3 first ones. So in the 3 first lectures, the idea was to kind of walk you through the basic machinery of thermal field theory, perturbative thermal field theory, and we did most of that in the context of just lambda 5 the fourth scalar field theory, and only in the end of the last lecture kind of touched QCD a little bit and also briefly talked about what changes then occur when we consider QCD and we introduce non-zero quark chemical potentials. But now we are going to make a big jump in a sense, and now in this last lecture we are going to be discussing the details of kind of contemporary research calculations and their use in the physics of neutron star cores, basically line of research where we are trying to figure out what so-called neutron stars are made out of. Are they made out of nuclear matter, or perhaps in some cases also deconfined quark matter? And the style of this last lecture is very different. I'm going to go a lot faster than so far, and I would advise you not to try to write everything down. I guess that the slides will be available then later through the website of the school, so you can consult them later, and of course you can, after the lecture, we can also discuss this, and you can ask all kinds of detailed questions. But nevertheless, the kind of 4 main references for what I'm going to be talking about are perhaps these 4 ones. The last one is the kind of reference 2 for the 3 first lectures as well, and the others are then research papers where we computed either performed detailed high order perturbative calculations in dense quark matter, or then performed the so-called model agnostic equation state inference, where we are trying to kind of piece all kinds of puzzles together or pieces of the puzzle together and really make robust statements about neutron star cores. So the parts of today's lecture are that I will start from a brief motivation into why we are doing what we are doing. Then I will say a few words about the kind of technical details that we skipped yesterday about how one can do perturbation theory at high density and small temperatures. Then I will say a few words about where we are right now, trying to complete the so-called next to leading order pressure for cold and dense quark matter, what the tools are we are using there. Then I will walk you through the most important neutron star observations that we can use in neutron star matter equation of state inference, and then finally I will present you some relatively new results concerning what the equation of state of neutron star matter actually looks like, and how likely it is to have deconfined matter inside massive neutron stars. Good. So let's start from the very basics. So neutron stars are old remnants of collapsed stars. So basically a massive ordinary hydrogen-burning star with a mass between roughly 10 and 20 solar masses. When it comes to the end of its life cycle, it explodes in a so-called supernova explosion, where the core then collapses together. The usual repulsion pressure is no longer able to keep the star intact, and then if the mass is just right, the end product of the repulsion will not be a black hole, but rather the gravitational collapse will stop just before an event horizon would form, and the end result is a star where between 1.2 and even up to a little bit over 2 solar masses of baryonic matter is squeezed inside a sphere of the size of Florence, more or less, a radius of roughly 12 kilometers or so. So these are incredibly dense objects. There are many ways you can kind of try to understand the density. One is that if you took the whole humankind, 8 billion people, and started squeezing us together, we would all have to be squeezed inside a sugar cube in order to reach the densities that you have in an average neutron star. No, not in the core where the density can be even like 5 times that, but just overall in a neutron star. And also the magnetospheres of neutron stars host actually the strongest magnetic fields, strongest macroscopic magnetic fields in the universe. You can, in so-called magnetars, the magnetic fields in the magnetospheres can reach up to 10 to 15 Gauss. Now you can of course ask a very natural question. So what can these tiny objects that are situated somewhere at least hundreds of light years away from us, in many cases much further, what can they teach us about the QCD length scale of 10 to 15 meters or so? And this is genuinely puzzling. The answer comes from general relativity. So these are the famous Tolman-Oppenheimer-Volkov or TOV equations that govern hydrostatic equilibrium inside neutron stars. There are two ordinary differential equations for three quantities, which are the mass within a radius of r from the center of the star, the energy density at that point, and the pressure at that point, in an approximation where we neglect the possible rotation of the star. So these are two equations for three quantities, and what that means is that these equations relate a microscopic relation, the equation of state of neutron star matter, the relation between the energy density and pressure, to a macroscopic relation, the relation between the possible masses and radii of neutron stars. So due to the huge density of the neutron star matter, the dominant interaction we have to take into account when we compute the equation of state is really QCD, the strong nuclear interaction. And if we are able to somehow theoretically compute what is the correct equation of state, we can plug that EOS, this relation, into the TOV equations, and out comes a well-defined mass radius curve. Or conversely, if we're able to perform many very precise measurements, simultaneous measurements of the masses and radii of individual neutron stars, so that we would be able to kind of observationally track this curve, we would be able to reverse engineer these TOV equations and obtain a unique, well-defined equation of state. In which one? So these, sorry, I mean, it just left out this, the pressure. Just pressure, yeah. Anyways, I mean, in theory, this is great, but then unfortunately, the problem is very difficult. So this is a plot from a few years back, from some review from a few years back, that was showing the predictions, the mass radius predictions from a bunch of phenomenological models for nuclear matter. And as you can see, the predictions were kind of all over the place. You get radii from something like 8 kilometers to 15 or 16 kilometers, and maximal masses from 1.3 to almost 3. So clearly, due to the issues that I was describing earlier, we don't have first principles tools from which we could compute the equation of state, and unfortunately also the observations are very difficult, which is understandable because we are talking about these tiny Florence-sized nuggets that are situated extremely far from us. So ordinary, like optical measurements, observations are of course out of the question. So this is sort of the setting. This is why it is somehow important to consider both from the side of QCD and particle and nuclear theory, and from the side of astrophysics, what can we learn about these objects, so that we would then be able to develop some kind of a systematic approach with which we one day could find out what's the right MR relation and right EOS. Yep. Sorry? Oh, these are just, those are details that are related to various types of kind of robust, either astrophysical or general relativistic limits, where we kind of know from first principles that these MR relations can't go into. So for instance, in here you would already have a black hole, and this I don't even remember by heart what that means, but it's some kind of limit where we know that the MR curves can't go. Good. So anyways, this is sort of the setting. The basic problem that we are trying to solve together with my collaborators is that we only have robust first principles tools to compute this equation of state here, given as the pressure of cold and dense QCD matter normalized by the free theory pressure as a function of the baryon chemical potential at two very different limits. We have chiral effective field theory and other robust tools of nuclear theory up to about 1 nuclear saturation density. so the density of one proton or one neutron. And we have then perturbative QCD that naively converges only when we are at something like 40 saturation densities or higher, and in between these two limits, exactly where the interesting stuff happens somewhere here, the kind of maximal densities of massive neutron stars and so on, we don't have any first principles tools, which is why kind of the traditional approach in the field has been to resort to various kinds of phenomenological models. But now what we have been propagating in the last 10 years or so is taking a very different approach, rather using astrophysical observations dictate what's happening in between. So the rough idea is that we kind of let the equation of state behave in any imaginable thermodynamically consistent and causal way in between these two limits, and then we try to use all kinds of observations of neutron star radii, masses, and so on to limit what can happen in between. And this has already led to very interesting and even rather impactful results. We have, in multiple occasions, derived the most accurate model agnostic EOS at all densities. So these bands you see here are the 1 sigma and 2 sigma predictions for how the equation of state looks like when you factor in all the observational information that we have. I will kind of walk you through this calculation later. And we have also made a case for the likely presence of quark matter inside massive neutron stars. Again, this is a plot where I will later explain what exactly is this DC quantity that we are showing as a function of baryon number density. So in some sense, the situation is already rather good, but we have not been able to kind of firmly answer questions like, is there definitely quark matter inside massive neutron stars, or what is the exact form of the neutron star matter equation of state or the mass radius relation? And this then, of course, raises the question: can we make like qualitative progress without just in any other way than just waiting and seeing when more and more accurate observational results come? Is there something that us QCD theorists can do to improve the situation? Yes. Yes, I'm coming there. Yeah, so this is one thing that I will cover. So just hang on a minute. And indeed, what I'm going to argue here is that we have a very unique opportunity right now. So this PQCD constraint, this sort of yellowish band we have up here at very, very high densities, this comes from a next to leading order, next to leading order equation of state for cold and dense quark matter, and we are now very close to finishing the next to leading order result, the N3 yellow result, which is this green curve here. And there's basically one parameter missing, one number missing from the full N3 yellow result. I believe we will be able to finish this calculation actually in a matter of months rather than years, and just plugging in natural values for that one unknown number, it looks like the accuracy, the precision of our result will improve by a factor of 3 or something like that. And this will allow either to shrink this high density band here or move the so-called matching point, where we go from the interpolated equations of state to this first principles equation of state to considerably lower densities. And what actually has enabled this very rapid progress is this so-called thermal loop tree duality technique, the father of which, or one of the three fathers of which, was supposed to be here, Pablo Navarrete, but maybe he will show up at some point. But it was really him, Kaapo Seppänen, and Risto Paatelainen from my group in Helsinki who came up with this kind of generalization of a vacuum QFT tool to a thermal setting that enables this calculation to be performed. But anyways, this is just the motivation for why we are going to be going through all these different topics today. And if there are questions at this point, please shoot. Yeah. Oh, yeah. So this is just kind of for illustration. So the idea is that like this band stands for all the possible equations of state of neutron star matter. So you can think of this band as being composed. I mean, it's literally composed of like millions and millions of individual equations of state. And for each of these equations of state, the center of a 1.4 solar mass neutron star lies at some chemical potential. The center of a 2 solar mass neutron star lies at some other density of chemical potential, and the same for the maximally massive neutron star. And yeah, exactly, the TOV means the maximal mass, and these bands are just, I think, 1 sigma bars for where, at which chemical potentials the centers of these three types of neutron stars lie. The reason we chose 1.42 and MTOVs is simply that 1.4 solar mass is kind of the canonical mass of a typical pulsar. So if you look at the kind of all mass measurements out there, huge majority of them are around 1.35 to 1.4. Yes, yes, yes. Yeah, absolutely. Yeah. I mean, this is precisely the reason why we need to do this interpolation. So we will never ever be able to kind of lower this point, this matching point down to the region where physical neutron stars lie. So the whole idea is that we can use the perturbative QCD equation of state as an ultraviolet or high density limit constraint, and then we can use things like causality and thermodynamic consistency to, and what one has, we have actually showed very robustly that what happens, what happens here directly affects what's happening here. So in like theoretically, I'll come back to this later, but like if for some reason we knew exactly what was happening, what the curve looked like in here, that wouldn't mean that we would be able to pin down the exact equation of state all the way here, but that would very dramatically narrow the range of possibilities at all densities. Good. But anyways, this was the motivation. This was sort of the reason why we are working on these things. But let me now get back to sort of where we left off yesterday and say a few words about how we in practice do this high order perturbative calculations that constitute this high density limits for the EOS. So again, we are back to where we formula that we have seen many times during my lecture. So basically the partition function of the path integral for the partition function of QCD, and now if we are working in the grand canonical ensemble, the quantity we get from its logarithm is the grand potential. That's a function of temperature, the U, D, and S quark chemical potentials, and the S quark mass. The reason I'm not including the U and D masses is that those are so small that we can approximate them to be zero, and the reason I'm not introducing charm or other more massive quarks is that the densities we're concerned with are low enough so that in practice is no charm in the picture. Now, kind of the challenge of perturbatively evaluating the thermodynamics of QCD matter from here is something that has been addressed for more than 50 years by now. And at high temperatures especially, there's a long history predating lattice simulations of computing these vacuum diagrams where we have gluons, ghosts, quarks, and then, as I mentioned yesterday, at some point you run into infrared problems. You end up having to perform some kind of a resummation or use a low energy effective theory and use that to perform a certain type of free summation, but then out comes basically a prediction, perturbative prediction for quantities like the pressure or the energy density as a function of temperature, if we are at zero chemical potential, or the entropy density or whatever. And long story short, things are quite well developed now. We can somehow qualitatively describe the lattice results down to temperatures of maybe 3 times the critical temperature of the deconfinement transition, 155. MEB, of course, the accuracy decreases or gets worse when we go to lower temperatures, and the lattice results are always the kind of preferred method or lattice QCD is the preferred method because it's non-perturbative and it can be used sort of to really act as the correct result to which we compare these perturbative predictions to. But then when we go to low temperatures, even the zero temperature limit and high chemical potentials, then the situation changes qualitatively. And the reason is that we no longer have lattice QCD available. We no longer have these data points that tell us the right answer. But we really only have PQCD and observations and so on to work with. So now I can ask, what are the main differences that happen in perturbative thermal field theory calculations when you exit the regime of high temperatures and go to the limit of high mu and vanishing temperature? Well, the first one I already mentioned yesterday. So because we no longer have Matsubara modes, that the Matsubara modes 2 pi nt or 2n plus 1 pi t, when t goes to 0, they get closer and closer to each other until the temporal momentum integrals become, or sums become continuous integrals. But now that we are working in non-zero chemical potentials, now we have this imaginary sort of shift plus or minus I mu that then affects how we can perform the contour integrals in the temporal momentum. There are also some simplifications. For instance, at zero temperature, if you have vacuum Feynman diagrams that don't contain any fermion loops, you can just throw them away because there's no scale, there's no chemical potential present, and since the temperature is zero, you know that you get scaleless integrals that vanish in dimensional regularization. But and moreover, what one typically does is start the calculation by somehow performing the temporal momentum integrals using the residue theorem, and then one ends up with three-dimensional so-called phase space integrals that then contain all the nasty possible ultraviolet and infrared divergences that one may end up having. Another kind of qualitative difference to high temperatures is then the fact that the infrared sensitive part of the theory is different. So as I briefly mentioned yesterday when we were discussing the infrared divergences that we saw in the lambda 5/4 theory, there one could somehow pinpoint that it was the zero Matsubara n equals 0 mode, the so-called static Matsubara mode of a bosonic field that was responsible for all infrared divergences. But this, of course, is no longer the case at zero temperature because there are no longer Matsubara modes. Rather, what one notices that it's a finite part of the four-dimensional momentum space that somehow is infrared sensitive. Basically, since we are working in Euclidean space, you can look at bosonic four momenta and conclude that all bosonic four momenta whose absolute value is smaller or of the order of the so-called Debye mass, which is basically a thermal mass, one loop thermal mass that the temporal gluon obtains at one loop order, they need some kind of a special treatment. And that then leads to the development of an entirely different type of an effective field theory than what one works with at high temperatures. I know that for some of you, this what I'm going to be saying next is sounds really gibberish. Don't worry about that. We won't be using that very much. But for those of you that have some experience from dealing with dimensionally reduced effective theories, the types of effective theories that we build at high temperatures for this zero Matsubara static bosonic field modes, I think this might be interesting to have a handle on how we actually do use this sort of low energy effective field theories at high density. So the first point here is that there are these two realms that are quite different. One is high temperatures, one is low temperatures. And maybe a bit counterintuitively, what really decides what is high and what is low temperature is a comparison between the temperature and not the chemical potential, but basically G times the chemical potential. So parametrically, this Debye mass, when you consider QCD at non-zero temperatures and chemical potentials, the Debye mass, the kind of dynamical mass parameter that the A naught field obtains, has the schematic form of g times square root of t squared plus mu squared, where g is the coupling constant of the theory, the gauge coupling. And as long as the temperature stays much larger than this scale here, we can still use these sort of simpler dimensionally reduced effective theories. But when T becomes of this order, let alone smaller than that, or goes to the zero temperature result, then we have to do something else. Now, as I mentioned, in this high temperature regime, the only modes that are infrared sensitive that need to be resummed, and that are thus the degrees of freedom in these low energy effective field theories, are the Matsubara modes of bosonic fields, meaning A0 and AI. While in the low temperature regime, all soft bosonic fields actually need to be resummed. So what one really needs to just look at is kind of the scale of the Four momentum of a field mode. And why this is, roughly speaking, can be at least qualitatively understood from this funny looking picture, which shows the individual Matsubara modes on this complex omega plane, where omega is essentially I times the bosonic Matsubara frequency. So at high temperatures, we have these individual Matsubara modes, and then this red circle here denotes this ME, the kind of debye mass scale, which says that whenever kind of frequency omega is inside this red circle, it needs some kind of a resum treatment. So what happens when you start from high temperatures of the order of the chemical potential, and then you start going down first to temperatures of the order of MD, and then all the way to the zero temperature limit, is at first you see that multiple of these Matsubara modes, not only the zero Matsubara mode, but some finite number of them fit inside this circle. And when you go to the true t equals zero limit, then these Matsubara frequencies morph into a continuous variable, and then you really have an infinite number of three-dimensional modes that need to be resummed, which is another way of saying that you need to resum a four-dimensional field. What the form of the EFT, low energy EFT, then is? Well, the simplest answer at high temperatures is these dimensionally reduced three-dimensional effective theories that are constructed for the zero Matsubara modes of the bosonic fields. I won't go to this direction in any detail, but just note that if you know these terms like electrostatic QCD, EQCD, or magnetostatic QCD, MQCD, then this is sort of the answer in this regime. On the other hand, if we are working at low temperatures or even in the T goes to zero limit, then this is not at all where you need to go. Rather, what we end up doing is we end up studying the low momentum or low energy limit of gluon 2-point functions, 3-point functions, 4-point functions, and then what we obtain after some relatively straightforward algebra is the so-called half thermal loop, or HTL effective theory, which is basically a low energy effective theory for all bosonic modes or gluonic modes in this case that satisfy that the absolute value of the Four momentum is at most of the order of this debye mass scale. Now we can then ask questions about how these effective theories contribute to physical quantities like the pressure. I think there was a question from one of you yesterday about what then happens when you really do these resummations, and essentially I won't be able to go to any real detail here, but it turns out that the lowest non-analytic or the lowest order contribution from these soft effective theories at high temperature, it basically comes from the non-interacting pressure of the EQCD effective theory, and it has the form of a three-dimensional integral over log of p squared plus me squared, which scales like g cubed, but then at zero temperature you have a four-dimensional kind of a higher dimensional space of infrared sensitive degrees of freedom, and there are also some other complications, like there's some type of an angular dependence that comes from the HTL self-energy, but nevertheless on dimensional grounds you can very easily show that the lowest order contribution from the half thermal loop effective theory to the pressure is of order g to the 4th log g. Then you can of course go to higher orders and perform weak coupling calculations within these theories, EQCD or HTL. I won't go into these details at all. This is already quite technically complicated. And what then, when you work through these calculations to high enough orders, what you see is at high temperatures this funny looking expansion where you have odd powers of G or non-integer powers of alpha S appear, and these are all due to this EQCD effective theory, the fact that you have a three-dimensional effective theory that then basically produces square roots of ME squared or terms that are proportional to ME. And this is one example of those. At high chemical potential zero temperature, you have a slightly simpler looking weak coupling expansion where the first non-analytic term in alpha S appears at order alpha S squared log alpha S. Then you have a double logarithm at alpha S cubed order, unlike in the case of high temperatures, and this is then something that has to do with the kind of properties of the half thermal loop effective theory. Actually, Loic Fernandez and Jean-Loic Kneur were able to predict the coefficients of these so-called leading log terms that are always of the form of alpha S to the power of n times log alpha to the power of n minus 1 to all orders from basically a renormalization group analysis of the half thermal loop effective theory. But anyways, I mean, that's kind of just scratching the surface of what's behind these low energy effective theories. If you're interested in this, then in the context of high temperatures, I can recommend this textbook of Mikko Laine and myself, but then at zero temperature, this kind of the literature is not nearly as developed. You can look at there's some kind of an introduction to this topic in the lecture notes that I wrote that I quoted already in the first lecture of my series. But then if you want to dig deeper, then you really have to consult actual research papers. This is basically a topic that's still under development. Most of our understanding on how to compute these soft contributions at order alpha S cubed only came about 5 years ago or so. So there haven't been really very well developed review articles or textbooks about this topic. But nevertheless, let me still go on. Let me now next address what we are doing right now. And this is again something I really don't expect you to kind of absorb any of the details, but I just kind of want to flash what kinds of challenges and calculations one then runs into when you go all the way to order N3LO in this weak coupling expansion. So if we now specify that we are working in the limit of exactly vanishing temperature, high chemical potentials, then there are three physically different types of contributions that can enter the weak coupling expansion of the pressure at all orders in alpha S. One are contributions from so-called hard modes. This means gluons and quarks that have momenta of the order of the baryon chemical potential or the quark chemical potential and which interact, so to say, perturbatively. So their interaction kind of produces a weak coupling expansion that's a well-defined power series in alpha S, no logs of alpha S or anything like that, and those can be obtained from just computing Feynman diagrams at various loop orders without any kind of a resummation. There will be undoubtedly infrared divergences here and there, but they can be dealt with in dimensional regularization and then be expected to cancel against other contributions. Then there are so-called soft modes, the gluons that have momenta of the order of the Debye mass g times mu b, and that interact so to say softly, and their physics is or their contribution to the pressure can be obtained by computing the pressure of the half thermal loop effective theory within a weak coupling expansion in that theory. And finally, and this part produces already logs of alpha s and so on. And finally, there is the technically maybe most convoluted part, which is the mixing of these hard and soft modes, and that only starts contributing at alpha order alpha s cubed, so it doesn't actually exist at the order alpha s squared, but only enters at an order higher than that. Now, the three first orders of this weak coupling expansion have been known for almost 50 years. So they're actually older than I am. They were computed by Friedman and McLaren in 1977, and this was quite a heroic calculation. And for instance, when I was kind of doing my PhD research, one of the things I needed to do then was to just redo the calculation, go through it, and I noticed that, I mean, but at that time in the late 70s, the numerics were so underdeveloped that they, for instance, were only able to compute even some one-dimensional, very elementary integrals to something like 2 significant digits, and in many places I noticed that something that they had given as whatever 7.48 and then 3 in inside parentheses was actually exactly 7.5 and stuff like that. But then when we go to higher orders, then already at this alpha s cubed order, then examples of all three types of contributions appear. And just as an kind of an anecdote, it's actually easy to understand from one figure what happens when one goes from one type of contribution to the other. So if you, for instance, just look at this for loop Feynman diagram, that is clearly of order alpha s cubed, because if you count how many vertices there are exactly six vertices in here. Each of them, so here is the father of the loop tree duality, so, or thermal LTDs. I was somehow searching you from the audience at some point. So you can compute this for loop diagram in dimensional regularization, and you just get some number times alpha s cubed. There will be infrared 1 over epsilons and ultraviolet 1 over epsilons, but in the way that we do these calculations, we just don't care about that, but trust that they will be cancelled later on. But here the assumption is that all of the momenta are of order mu b. But now if this doesn't hold, if this assumption is untrue, and for instance this gluon line in here, this one that goes from here to here and continues here, if that becomes soft, then what happens is that you notice that each Feynman graph like this contributes at the same order as this one. So you can basically dress this soft gluon line with an arbitrary number of gluonic one loop self energies, and each of those, as long as the gluonic momentum is soft, each of those insertions of another fermion loop here contributes at the same order alpha s cubed. Well, there's a simplification. The simplification is that when this gluon line is soft, you don't have to include the entire one loop self energy here, but it suffices to consider the HTL limit of the gluon 2-point function, and moreover you can resum these types of diagrams so that you end up with a diagram, a tree loop diagram that contains one, so to say, hard thermal loop resummed gluon propagator. So here you have then an example of a mixed contribution. This is a contribution where you have one soft line and then all the other propagators are still hard. We assume that their momenta are of the order of the baryon chemical potential. But again, you can play this game. You can ask what happens if this gluon line or this gluon line become soft. Well, in that case, you have to resum them too, and you even have to resum the vertices where three soft gluon lines meet, and then it basically it looks kind of horrible. It amounts to resumming all diagrams that look like that, but actually there's a simplification. This then produces, when you resum both these two remaining gluonic lines and the two vertices, this contribution becomes a two-loop vacuum diagram that you can compute within the half thermal loop effective theory, and this two-loop diagram there then just produces this soft, part of this soft contribution to the pressure at order alpha is cubed. Now I won't bore you with all the details that go to these calculations. I'll just kind of quickly flash some references. The leading log alpha is cubed times log squared of alpha was computed in 2018. Then the soft contribution was first computed in 21, the one that comes from purely from these two-loop HDL graphs. Basically, we calculated these three diagrams. Then the mixed part was first finished in QED in 23, very early 23, and then quickly generalized to the case of QCD. Later that year, that computation by Tyler Gorder, Risto Paatela, and Saga Säppi and Kaapo Seppänen was already quite a bit more involved technically. It kind of necessitated the explicit evaluation of a bunch of these mixed type Feynman diagrams, and that is exactly the computation that led to this result that basically shows that if this one unknown coefficient that comes from the purely hard sector has more or less the right value, then the accuracy of the final result for the pressure will dramatically improve. But then there is this hard part, and this really is the kind of the thing that we have now been battling with for several years, that involves evaluating all of these 40-something Feynman diagrams, and this constitutes quite a non-trivial challenge. Basically, a bunch of these diagrams are easier than others, but then there are also ones that really kind of their evaluation necessitates the development of genuinely new tools, and this is I was initially thinking that I would introduce this loop tree duality concept in my lectures here, but then I realized that might be a little bit too much here. But nevertheless, let me just say that computing these four loop diagrams sort of one by hand would never ever lead to sort of the correct result in a finite amount of time. One has to automatize the computations to a very high degree, and this is precisely where Pablo is really the guy performing the heavy lifting. We have been able to collapse the sort of, if you just use Feynman rules to write down some kind of a list of mastery integrals, superficial mastery integrals from here, then we end up with Pablo, can you remind me how many hundreds of thousands or no, but I mean before you do all your tricks, something like 100,000 sort of independent integrals, but then he's able to do his black magic and collapse this number down to about 100 or so kind of masters. But even then, it's we've been able to show that the infrared divergences that appear from these masters, those can be isolated and they exactly cancel the infrared divergences that come from other parts of the calculations. But even then, it's really a gruesome challenge to try to get numbers out of these guys. And then there is this new technique that I won't be really discussing today called thermal loop tree duality, which basically is just an algorithm that allows one to turn this huge list of very complicated, basically 16-dimensional integrals into an ultraviolet and infrared finite entity that can be dealt with numerically using Monte Carlo methods. And we have already successfully shown, or I should rather say that Pablo and Kaapo Seppänen have already shown that the most difficult ones of these are or they have already computed the most difficult difficult integrals from here, and there's still something left to be done, but I guess that we can more or less promise that by this summer this will all be done, and we will have that one number C naught that is here set to a value that is somehow considered the most likely one through a Bayesian analysis, but we really don't know the value of this number yet. So this is at this point just a guess. But anyways, I think this is a very natural time to keep a 10-minute break, because next I'm going to switch gears altogether and go into neutron star observation. So let's come back in 10 minutes at 10 and then continue from there. Okay, I guess almost everybody's back, so we can then continue. So now that we covered the basic idea of this kind of EOS inference and the different limits that are known robustly and so on, let's next look in more detail at the data, the neutron star observational data that we can use in this inference process before we then go all the way to the final results. So the most basic quantity that one can measure regarding neutron stars are their masses. There's a long history of using various types of GR effects to infer the masses of two components in a binary system, for instance, and there are these large libraries that nowadays exist that just list various pulsars, various neutron stars and their masses with some I think 2 sigma error bars that are shown here. And from these individual data points, the by far most useful measurements from the point of view of EOS inference are the masses of the most massive neutron stars in existence. And here there are 2 data points all the way up here that denote 2 stars that have masses that are believed to be of the order or slightly above the 2 solar mass limit. So we can fairly safely say that the TOV mass, but by definition, which is the largest mass of a stable neutron star, is above 2 solar masses. Why this is important? If you recall this figure that I showed to you in the beginning of my lecture, which shows basically the MR predictions of various models for nuclear matter. What these 2 data points allow us to do in practice is draw a straight horizontal line at 2 solar masses and then throw out every single EOS that somehow doesn't reach this point. So each of these mass radius curves typically ends at a certain point where either there is a strong first order phase transition that destabilizes the star, or then just the central density becomes so high that the star becomes unstable with respect to radial oscillations and collapses into a neutron star. And for those model EOSs that predict a maximal mass below 2 solar masses, we can basically say with confidence that those are ruled out. Those cannot be physical. Now, of course, you can ask, how about radius measurements? And this is then already a much more complicated story, given the fact that neutron stars are so incredibly small, of the order of 10 kilometers or 12 kilometers in radius. It's very non-trivial to measure the radii or the radius of an individual neutron star, and rather what one does is people build models for the atmospheres and magnetospheres of neutron stars, and then study basically X-ray radiation coming from the stars, and then try to kind of analyze from the results what the most likely value of the radius of a given neutron star is. There's a lot of money involved in these experiments. A particularly famous observatory is called NICER, which is situated at the International Space Station, and it's doing so-called pulse profiling measurements of a handful of different neutron stars. What typically comes out from these individual measurements are kind of 1 sigma and 2 sigma contours like this that have slightly different shapes depending on the exact method used and the exact star used. They typically none of these measurements alone is super constraining, but by now there are already dozens of individual neutron stars with sort of non-trivial 1 sigma and 2 sigma limits measured, and then when these are all taken together in a Bayesian calculation, then already one gets a signal, and that signal appears to point towards the neutron star radius, typical neutron star radii being in the ballpark of 12 kilometers. And just to kind of give you a feeling of the accuracy in this business, when I first attended a neutron star workshop, I think that was 2009 or something, there was still a debate between whether there can be neutron stars with radii below 10 kilometers or radii above 15 kilometers. There was, don't ask me for the details because I don't know that at all, but there were basically two camps, one claiming that neutron stars are very compact with radii in the ballpark of 9 or 10 kilometers, and then there was another camp saying that they are much larger with radii of 2 or 15 kilometers, and well, when all the dust settled, then it turns out that neither was really right, and the kind of correct value is somewhere in between, around 12 kilometers or so. Good. But then, of course, there is still a third class of observations that we can use in EOS inference, and this is probably the most famous one. So now I'm talking about the first gravitational wave measurement from a binary neutron star merger that was made on August 17th in 2017. And since then there have been many. Now it's not only LIGO and Virgo, but CAGRA as well, and they are undergoing, I don't even remember how many observations run at the moment, but nevertheless they have been able to record dozens and dozens of binary gravitational waves from binary neutron star mergers. Now there are, every time we have such a measurement, such an observation, there are in principle 3 types of independent observational data that we can use in EOS inference. The first one, and probably the one that you are the most familiar with, has to do with the in-spiral phase of the merger. Basically, the process where these two neutron stars are getting closer and closer to each other, they are going around each other at a frequency that increases in time, and when they get close enough to each other, then the intensity of the gravitational waves that are emitted grows very, very rapidly until at some point the two stars actually collide and produce a post-merger system. So it's exactly this in-spiral waveform that LIGO and Virgo and CAGRA have been able to measure from several mergers, and the good news is that since this in-spiral waveform deals with the part of the merger where the two stars haven't actually collided with each other yet, the system is still cold, so we can obtain information about the properties of cold and dense matter, which is basically what I've been talking about here. But the downside is that then, like, there's a lot of information that is contained in the so-called post-merger waveform that we haven't been able to record yet because the associated frequencies are so high. And finally then, there is a possibility always to measure an electromagnetic counterpart, a kilonova or a short gamma ray burst, and these then give their analysis typically involves some astrophysical modeling. One has to be able to deduce whether, for instance, the gamma ray burst signals the gravitational collapse of the merger product into a black hole, but with some kind of caveats, this can increase the amount of information that we get from one single merger. So let's then look at these 3 types of potential inputs one by one. So tidal deformability, first of all, that really describes tidal forces. So it's the same phenomenon that causes tides on Earth, and but the only difference being that the tidal forces between these two incredibly compact and massive neutron stars that are kind of running around or encircling each other in a very, very rapid pace, then the tidal forces are enormous, and they actually are able to basically change the shapes of the two stars. So what really happens when the stars are going around each other is that the gravitational pull from the partner always makes the shape of the star undergo a motion where it's sort of it's no longer a perfect sphere, but it sort of always stretches in some direction, and this stretching and these tidal effects actually have a measurable effect on the in-spiral gravitational waveform that is then measured on Earth. So of course the way this goes is that people have been doing numerical simulations of what various kind of, I mean the question really is how much do this, well, from the waveform we can basically deduce how much these two stars are deformed or their shapes are deformed, and then on the other hand this so-called tidal deformability, it's really a function of the material properties of the system. So basically the idea is that it's a quantity that can be computed from the equation of state of neutron star matter, and one can then do simulations with tidal deformabilities of various sizes, and then upon comparison with the measured in spiral waveform, one can basically give lower or upper limits for this one parameter called tidal deformability that by definition is defined in such a way that if an object is immersed in an external quadrupolar field epsilon ij, then minus lambda times epsilon ij is the quadrupolar component that the star's own gravitational wave develops, this qij. And now it turns out that the tidal effects in the waveform that was observed in this 2017 merger that still continues to be the highest quality measurement that we have to date, they turned out to be fairly small. So what one could take away from the LIGO and Virgo measurement was that the tidal deformability of a 1.4 solar mass neutron star is between 70 and 580 in these particular dimensionless units at 90% likelihood. And out of these two limits, the 70 is actually almost trivial. It's very difficult to come up with a viable equation of state that would have a tidal deformability or predict the tidal deformability even lower than that. But this upper limit 580, this actually turns out to be a very useful one, and that can be seen to actually correlate very strongly with the radius of a star of this size. So what actually we were the first group to be able to use this in equation of state inference, and we were able to show that this upper limit actually amounts to a very non-trivial upper limit for the neutron star radius, which was, I think, 13.5 kilometers, which was the lowest upper limit that had been derived in 2018, because these NICER and other results were not available then yet. Then next, there is this post-merger waveform. So unfortunately, as I mentioned, this is something that hasn't been observed yet because the frequencies are so high. But the hope, of course, is that when these so-called third generation gravitational wave observatories like the Einstein telescope and the Cosmic Explorer will become active in the 2030s, then we would have a clean measurement of also the post-merger waveform. And this there now the physics is very rich and in some sense much more interesting than for the in-spiral phase, where we just have these two distinct objects going around each other and kind of causing tidal forces on each other. So when the two stars actually merge together, when they touch each other, that starts a very complicated out of equilibrium dynamics. that can be modeled with relativistic hydrodynamic simulations. And we know that there are 4 distinct scenarios that can occur. The simplest one that basically takes place when the 2 stars are sufficiently massive is that the total mass of the remnant is so high that one has an almost immediate so-called prompt collapse into a black hole. And here the time scale is only some milliseconds, and typically there is no real electromagnetic counterpart in this kind of a case. Basically the 2 stars touch each other and whoomp, they just form a black hole. Nothing interesting happens. But then there are two other scenarios, the so-called hypermassive and supramassive neutron star scenarios, which are much more interesting. In both of these cases, a more long-lived system, a system that lives some hundreds of milliseconds or some seconds, is formed, which is this so-called differentially rotating system, where basically there's no uniform rotation speed for the entire system, but it undergoes differential rotation, and then it can either collapse into a black hole in a matter of roughly 1 second or less, or it can continue rotating and form a uniformly rotating supramassive neutron star that then is much more long-lived. It can live for hundreds or even thousands of seconds and then collapse into a black hole when it has lost enough angular momentum, because a very rapidly rotating system actually, well, this is very intuitive, but if you have a system that's rotating extremely rapidly, that rotation kind of shields the system from gravitational collapse until the rotational speed has gone down enough, and then there is again likely a collapse into a black hole. And then finally, there is a very unlikely but still possible scenario number 4, in which case there's never a collapse. So there's first a hypermassive phase with differential rotation, then a supramassive phase with uniform rotation, and then the system just keeps on rotating. And what happens when like years and thousands of years and millions of years kind of goes by is that the end product is simply a more massive neutron star. And this may well be the reason or the mechanism behind the most massive known neutron stars, the neutron stars with masses around 2 solar masses or so, because it's a little bit of a problem how to create such massive stars in supernova explosions. But nevertheless, these are the possibilities, and when we will see gravitational post-merger gravitational waveform measured, then we will be able to typically tell which one of these scenarios actually took place. Now, this is a huge business. There are many groups doing relativistic magnetohydrodynamic simulations of neutron star mergers, and the hope is that since this dynamics is now, of course, on the microscopic scale, it's dictated by the microscopic properties of the medium, the finite temperature and finite density equation of state. You can actually have tens of temperatures of the order of tens or even close to 100 MeV occur. Transport effects may be sizable, especially the bulk viscosity of nuclear matter and quark matter are important for the dynamics, and you can have very interesting things like some parts of the system may go through the deconfinement transition multiple times, because there are all kinds of density kind of fluctuations in the system and pulsations, which may actually kind of force the system to cross a possible first order phase transition line on the QCD phase diagram multiple times, and then of course the hope is that when one does these sort of very complicated simulations with various types of equations of state, some containing a first order phase transition, some containing only a crossover, and in some cases there's a larger and in some cases smaller bulk viscosity involved, then we would be able to, once the actual post-merger waveform is measured, one would be able to compare its properties with these simulation results and really make robust statements about the finite temperature properties of dense QCD matter. And as I mentioned, there are many different groups working on these topics. One of the leading ones is that of Luciano Rezzolla in Frankfurt, and this plot is from one of his past papers. But good. Then let me still, before going to my results, go through this last possible signal that we can obtain from neutron star merger, which is a possible electromagnetic counterpart. So here it's interesting to note that in this cleanest and highest quality sort of neutron star merger that we have observed so far, GW170H17, there was a very clear electromagnetic signal. There was a short gamma ray burst that came more or less 1.7 seconds after the gravitational, well, after the peak of the gravitational wave signal, which is when the two stars actually collided. And now there has been some debate about this. I'm not an expert of this kind of numerical GR and the astrophysics of neutron star mergers, but the consensus in the field is that this gamma ray burst 1.7 seconds after the merger after the two stars touched each other signals a delayed collapse to a black hole, so that there was a collapse eventually. This scenario 4, that there would just be a neutron star left, was ruled out, but also the prompt collapse scenario was ruled out because there was this 1.7 second delay. So this basically leaves two possible scenarios: the supramassive scenario, where there is a long-lived kind of uniformly rotating system, and a hypermassive scenario where the system collapsed into a black hole when it was still differentially rotating. Now, these are both extremely interesting scenarios because they allow us to derive an upper limit for the TOV mass of a non-rotating neutron star. The maximal mass of a neutron star, the values that come out from these two scenarios are about 2.5 solar masses in the supramassive scenario and about 2.2 solar masses in the hypermassive scenario. And the consensus seems to be that the hypermassive scenario is the preferred one, which actually leads to very strong and interesting constraints for both the TOV mass and the equation of state. This is something that was first pointed out by Rezzolla and company. Good. Are there any questions at this point regarding these observations? So yeah, okay, very good question. I kind of skipped that. So M Kepler is the maximal mass of a maximally rapidly rotating neutron star. So if you have a given equation of state and you consider basically you have a neutron star composed from some equation of state that has some well-defined mass, you can start rotating it. So actually, let me say this in another way. Say that we have a fixed equation of state, and then there is a TOV mass that corresponds. That's basically the maximal mass that this particular equation of state is able to support when there's no rotation. Then you start rotating the star with different frequencies, and you will, just solving the TOV equations in a rotating case, you will notice that the maximal mass actually increases with increasing rotational frequency, and this basically because the centrifugal force in some sense is kind of helps keeping the star intact. So then you can just keep increasing and increasing and increasing this rotational speed until you end up in a point where the surface of the star is rotating at the velocity of light or speed of light more or less, and the whole system kind of disintegrates, and that kind of maximal rotational frequency where the star is still intact corresponds to the maximal mass of that this equation of state can support in any circumstance, and this maximal mass is then called the Kepler mass. And this is actually, say that for a given equation of state, this MTOV is 2.1. Then this M Kepler can easily be 2.3. So it's a substantial effect if you allow the star to rotate maximally fast. And this is actually where these two inequalities come from. In the supramassive scenario, the idea is that the system at some point rotates uniformly and then collapses into a black hole. This means that the TOV mass, this means that the remnant has to have a mass that's larger than the TOV mass. Otherwise, there would never be a collapse. I mean, you agree? And similarly, then in this hypermassive scenario, we can make a stronger statement, which is that the Kepler mass has to be, the remnant mass has to be larger than the Kepler mass, because if the remnant mass was smaller than the Kepler mass, then the system would enter this kind of uniform rotation phase, where it then, by definition, would be a supramassive neutron star. I know that this is kind of non-trivial, but the point is that this M Kepler is the absolute maximal mass that a uniformly rotating neutron star can have when its rotational frequency is maximal. And if we know that the star or the remnant in a given neutron star merger collapsed into a black hole in the hypermassive phase before the system started rotating uniformly, we know that the remnant has to have a mass larger than M Kepler, because otherwise it would have entered the uniform rotation. But yeah. So anyways, the main point for my argument is simply that this fact that we had the gamma ray burst signal, it actually gave us extra information. It gave us information about the maximal mass of non-rotating neutron stars. Good. So then for the last 30 minutes or so, let us actually go to the sort of main topic of today, which is the use of the PQCD results in this model agnostic equation of state inference. So again, what's the basic idea in here? The basic idea is that we have these two limits where we robustly know what the equation of state looks like. In this figure, the normalized pressure of cold and dense QCD matter given as a function of the baryon chemical potential. There is this tiny red segment here where nuclear physics chiral effective field theory gives us the kind of right ab initio answer for the pressure, and then there is this segment at very, very high densities where PQCD is converging, and we know where the curve has to end up in. But now, since in between we are kind of clueless, we can do phenomenological models, but then there are all kinds of uncontrolled uncertainties. What we then can alternatively do is we can fill this space or this interval from something like 1 saturation density to 40 saturation densities with all kinds of functions. We can use, in principle, any type of an interpolator we want. The simplest ones that are typically used are the use of piecewise polytropes or piecewise speed of sound interpolators, but then you can also have some kind of a complete set of basis functions that go all the way from here to here. But the idea is that you build large families of possible equations of state, and when I say large, I mean millions of potential equations of state that connect at low density to this red part and at high density to this orange band. And what you require for each of these equations of state is that they smoothly, the individual curves indeed smoothly match to the low and high density phases. The pressure is always continuous as a function of mu b. Nb, the baryon density, is either continuous or can be allowed to jump once if there's a first order phase transition. We of course require subluminality. We require thermodynamic consistency. All basic thermodynamic relations need to be satisfied. And finally, the crucial thing is that once we have a family of say 3 million neutron star matter equations of state that we are happy kind of cover all possible behaviors of this that this equation of state may have, then we use observational data to discriminate the ones that the equations of state that better fit fit the observations from those that don't. So as a trivial example, we compute the maximal mass of neutron stars for each and every of the equations of state that compose our ensemble, and then we somehow, either in a Bayesian way or with hard cuts, we throw out or assign very small likelihoods to those equations of state that predict that the maximal mass of neutron stars is below 2 solar masses. So this can be, as I mentioned, this can be done in many ways. There are also non-parametric alternatives, but what we have found the most useful parametrization for this kind of interpolated equations of state or inferred equations of state is to start from the speed of sound as a function of quark or baryon chemical potential, and assume that the true behavior of the speed of sound in nature can be approximated with a piecewise linear function of chemical potential. So we just divide this chemical potential interval from the nuclear physics regime to this PQCD regime to some number, typically 6 or 7 or 8 parts, and then we just construct this kind of spiky looking piecewise linear speeds of sound, and we integrate the speed of sound to obtain then the equation of state, the pressure as a function of chemical potential or energy density or number density. Why do we do this? There are many reasons, but one of the main ones is that this allows us to keep track of the speed of sound, of the behavior of the speed of sound in this system, and in this context, it's actually interesting to note that kind of in this business, in this kind of neutron star matter equation of state inference activity, it really resides kind of between two different communities. So on one hand, we have models for nuclear matter that have been used for decades to study neutron star matter and build mass radius models and whatnot. And in these models, typically the maximal value for the speed of sound is very close to unity, or in some cases, in some very widely used cases, actually exceeds the speed of light. So they are acausal. On the other hand, then we have this very well-known, well-studied system of hot quark-gluon plasma, where lattice simulations have shown us that the speed of sound actually never exceeds the conformal value, which is 1 over square root of 3. It has a non-monotonous behavior at low temperatures. This is at zero chemical potential, but then it rises towards the conformal limit 1 over square root of 3 in a monotonous way and never exceeds this limit. And why this is important is that at high densities and zero temperature as well, we know that when you go to asymptotically large densities, the speed of sound has to approach 1 over square root of 3 from below. So this is actually dictated the way what happens at asymptotically high temperatures or densities, asymptotically high energy densities, is dictated by the sign of the QCD beta function. So in the non-interacting limit, the limiting value of the speed of sound is 1 over square root of 3, and the sign of the QCD beta function tells us that the approach has to come from below this quantity. So yeah, it may be that at low densities this is what happens for the speed of sound, but then at some later point this curve has to bend down and then again start rising towards this 1 over square root of 3 value, which lies somewhere around here. So anyways, I mean, the fact that we can track in this equation of state interpolation, the fact that we can track the possible behaviors of the speed of sound is quite interesting. Now, I won't go to any technical details in how we do this sort of, how we in practice do this statistical analysis and how we construct the stellar models from the equations of state and so on. But I will only show this result from a paper that we published in 2020. or this is sort of the starting point of my discussion. This is the result of a very simplistic calculation where we just used hard cutoffs. We demanded that every equation of state that we allow to be in our ensemble has to be able to support 2 solar mass neutron stars, and every single equation of state has to be compatible with the 90% tidal deformability upper bound that LIGO and Virgo provided for this GW1708 17 collision or merger of two neutron stars. So what you see then here is our resulting band for the viable neutron star matter equation of state. So the equation of state has to be within this kind of funny looking sausage in here, but the extra information that is given by color coding is that if we had some way of telling that the maximal value of the speed of sound squared has to be below something non-trivial. I mean, of course, it has to be below 1 everywhere, but if we had extra information from somewhere that it can't, CS squared cannot exceed, say, 0.6, then you would be able to say that this darker green middle of these bands, that the equation of state has to be within it, and the extreme case is then that if we're able to say that also at high density and zero temperature, this conformal limit of 1 over square root of 3 for the speed of sound, or 1 over 3 for CS squared, cannot be violated anyway, then we would be left with only this dark, almost dark blue band in the middle. In that case, we would very accurately know how the equation of state behaves at all densities. But moreover, these are just 2 very, very conservative data points that we used there. There are also others that one can use. And in 2022, we took into account two further data points. One that corresponds to a lower limit for the neutron star radius, for the radius of a roughly 2 solar mass neutron star from the NICER collaboration. They said that the radius of a 2 solar mass neutron star has to be at least 11 kilometers at 95% credence, and at least 12.2 or at least 12.2 kilometers if we only impose 1 sigma uncertainties. Also, we as I mentioned, we know with very high likelihood that that there was a delayed formation of a black hole in this GW1708-17 merger, and that happened either via the supramassive or the hypermassive scenario, where the hypermassive is considered more likely and leads to more stringent bounds, while the supramassive case is kind of that can very safely that can be taken to be the case in a very conservative scenario. So at least there was a supramassive scenario, but there even might have been a hypermassive scenario. Okay, so what happens if we take this kind of additional information into account? If we want to be super conservative, we only use this 11.0 kilometer lower bound for the radius of a 2 solar mass neutron star, and we employ the supramassive scenario. And then what comes out is here the dashed line corresponds to this initial band, and what you can now see is that we are able to rule out some parts of previously allowed equations of state in here, and some other parts down here. But if we are even more brave, and we actually use the 12.2 lower limit for the radius of a 2 solar mass neutron star and the hypermassive scenario, then we see that all that is left is this very, very tiny band of viable neutron star matter equations of state. And what is maybe interesting to note here is that the parts in both of these cases, the parts that of this allowed equation of state space that were ruled out by these extra observations, they actually correspond to regions where the maximal value of the speed of sound has to be very high. So even in this kind of extreme case, we still allow almost all of those low speed of sound EOSs that formed the band in this initial 2020 result. So this is certainly curious. This here, by the way, represents sort of a kind of medium conservative estimate. This was our kind of main result from the 2022 paper, where we employed the supramassive cut and also 11.4 kilometers for the radius of a 2 solar mass, lower limit for the radius of a 2 solar mass neutron star. So anyways, this is sort of what you get from these types of hard cut analysis, and it seems like the true behavior of the equation state has to be somewhere here. And now I would at least argue that the most curious thing about this figure is the fact that you can almost take two straight lines, two rulers. You can, if you continue from this low density equation state band with more or less the same slope it has here. This red line has a slightly higher slope than the chiral effective theory band here, but not much. And then you, on the other hand, extrapolate down from high densities with the same slope that this PQCD band has. You kind of end up with a rather good approximation of the overall shape of the band. And moreover, the point where these two lines meet, the point where there seems to be some kind of a qualitative change in the slope of this equation of state band, that turns out to take place at an energy density that's clearly lower than the energy density, the kind of epsilon TOV value, the energy density that occurs at the center of a maximally massive neutron star. So this basically prompted us to speculate that maybe we can somehow associate this change in the so-called polytropic index of the equation state with a deconfinement transition, and then we came up with a criterion based on the values of this gamma. We basically said that if gamma is below 1.75, the system is near conformal, and we interpret that as quark matter, and if it's above 1.75, we say that that's non-conformal and hadronic, and then we just, this was kind of a not very robust, but more or less for the fun of it, we then looked at what would happen, and what happened was that we saw that for low speed of sound, low maximal speed of sound equations of state, there would always be a sizable quark matter core, and the only way to kind of compose fully hadronic maximal mass neutron stars would be to have an equation of state that basically reaches this one, or where the speed of sound almost reaches unity at some density. But anyways, this is just a very indicative result. There are certainly many questions that this kind of a naive analysis leaves unanswered. One is, are there other quantities besides this polytropic index that display somehow signs of conformalization? I should maybe mention that this gamma equals 1, that corresponds to this blue slope here. That is the result you obtain in a conformal system, one of which is a high density quark matter. You could also ask, does conformalization imply deconfinement, or could this be just a shift from one phase of nuclear matter or hadronic matter to another one? Maybe this could correspond to the onset of hyperons in the system or something like that. You can also ask, how likely are the quark matter cores? Can we do some kind of a probabilistic analysis and say that the likelihood of quark matter cores being present in maximally massive neutron stars is at least, I don't know, 50% or 70% or 90%. And then finally, you can ask, does this PQCD limit at the high densities play any role in this business? So to answer these questions, we then in 2023, we decided to perform, or actually we decided this much earlier, but this calculation just took a long time. We decided to abandon these hard cuts in our analysis, which are kind of nonsensical, because they would basically just they would discard an equation of state that has a maximal mass, predicts a maximal mass of 1.99 solar masses, but allow one that that has a maximal mass of 2.00. Rather, we used the Bayes theorem, and we did a probabilistic calculation where we also not only studied this gamma, the polytropic index, but also many other quantities such as the speed of sound, the conformal anomaly that's oftentimes used as a measure of conformality in hot quark-gluon plasma, and finally also its logarithmic derivative with respect to the energy density, for the reason that we might have a situation where delta passes through zero, but then becomes large and negative, in which case the system would kind of pass through a conformal behavior, but then become non-conformal again. And finally, we also use two different ways of performing this interpolation, one being the speed of sound interpolation and the other non-parametric Gaussian process regression. So what we really wanted to do is to obtain kind of hard limits or probabilistic limits for how different quantities behave on one hand or at different densities, and then we would be able to, we wanted to compare the results we get to known robust results in different limits, like chiral effective field theory, in different phenomenological models for dense nuclear matter, values that one obtains in perturbative quark matter, or in conformally invariant field theories, or in systems that are undergoing a first order phase transition. So what were the main results? The first one, maybe in some sense the most important one, is that indeed all quantities that we tracked conformalized before the centers of maximally massive neutron stars. So you can see from here, this is the baryon number density, and here are the centers of 1.4 solar mass neutron stars, 2 solar mass neutron stars, and maximally massive neutron stars, and you can see that our 1 and 2 sigma error bars are very nicely centered around the conformal value for CS2, the same for gamma around unity, and same for delta around 0. We spent some time trying to decide if we could come up with one quantity that would really track how the system conformalizes, and we ended up choosing something that we call a conformal distance, DC, which is the square root of delta squared, the normalized trace anomaly squared plus delta prime squared, which has the nice property that if this DC goes to 0, then it forces all quantities that we are tracking to go to their conformal limits. So gamma has to go to 1 to unity, CS squared has to go to 1/3, and both delta and delta prime have to go to 0 if this DC vanishes. Also, we noted that the limits that one obtains in models of nuclear matter and in perturbative QCD are sufficiently far apart so that we can really have a limiting value for this DC, where we say that if the system is above, if the DC value is above a certain limit, we are likely in sort of non-conformal or hadronic matter, and if DC is below some limit, we are very close to conformality. Now we chose as the limiting value 0.2, that is actually very conservative. That's far away from the lowest values one obtains in any model for confined nuclear matter, and actually in PQCD even you might get values slightly above this 0.2. So the fact that we only call something near conformal matter when DC is less than 0.2 is being very conservative. Now we could ask then what's the likelihood of us residing or likelihood of DC being smaller than 0.2 in the centers of different mass neutron stars. The results were that for 1.4 solar mass neutron stars we got exactly 0, saying that the system is definitely non-conformal. For 2 solar mass neutron stars this value is about 11%, and for maximally massive neutron stars we obtained almost 90%. And two crucial things. One is that one can ask what happens for the remaining 12%. Well, they all turned out to exhibit first order phase transition like behavior. So it seems that the only alternative to having the centers of maximally massive neutron stars behaving very close to conformal matter is that the system is undergoing a first order phase transition. So the phase transition is then what destabilizes the neutron stars. And second, this new criterion is extremely conservative in comparison with our 2020 gamma smaller than 1.75 criterion, which is just demonstrated by the fact that if we had used the old criterion, this 88% limit would have actually turned to 99.8. In any case, this just signals that one can safely say that it's likely, it's not certain, but it's likely that the centers of maximally massive neutron stars behave in a near conformal way. Then, of course, you can ask whether conformality or near conformality signals deconfinement. This is more non-trivial. This is certainly, I mean, well, there's no proof for this. The one thing that one can say is that the value of the pressure divided by or normalized by the free theory pressure in this regime where we are at the centers of maximally massive neutron stars, the value of P over PFD is about 0.4. So the pressure is about 40% of its value in a non-interacting theory. You can compare this to the case of high temperatures where the Stefan Boltzmann non-interacting value for P over T to the fourth is here, it's 5 point something, while we know from lattice simulations that the deconfinement transition happens around 155 MeV, meaning it happens somewhere. So 300, 100, it happens somewhere around here where actually P over T to the fourth is less than 1. It's way less than 20%, way less than 0.4 if we give it in the same units as we use here. So, I mean, you can make of this what you want, but I would myself say that near conformal is quite likely the same thing as deconfined in this case. Finally, we used other methods as well. The results I showed so far were for the speed of sound interpolation. When we used Gaussian processes, the results were almost identical. In this case as well, the likelihood of near conformal matter inside TOV stars was of the order of 80%. But one very nice feature of this Gaussian process method that was developed by Aleksi Kurkela, his student Oleg Komoltsev and Tyler Goda in this work, was that there one could treat this high density PQCD limit as in the same way as different observations. So one could kind of turn off the PQCD bound at high densities, and then one can literally show that the PQCD limit plays an important role in softening the equation of state considerably, and what one effect or one way to characterize this effect is that if they turned off the PQCD bound, the likelihood of near conformal matter in maximal mass neutron stars was about 50%, while it was about 80 when they used the PQCD limit. Now, finally, I would say that there's one important caveat that's remaining, and this is related to strong first-order phase transitions. So far, all the results I've shown have been derived using equation of state ensembles where we mimic first-order phase transitions by arbitrarily rapid crossovers, but there are some indications that for very strong phase transitions, this is not a good approximation. And this is something we are working on. We actually have a recent paper with Sofia Blomqvist, Christian Ecker, and Tyler Goda, where we are using a new ensemble that includes first-order phase transitions, and we are there studying twin stars, but we are also working on kind of a general phase transition analysis. There's one already that Oleg Komoltsev did using the Gaussian process method, but this is here the jury is to some extent still out. It may well be that there are important effects that come when we allow very strong first order phase transitions. Anyways, this then brings me to the very last slides. Just a couple of last words regarding what I've been talking about today. So this application of the perturbative QCD calculations in the inverse of the neutron star matter equation of state is a field that has been growing in the last 10 years very rapidly. We were the first ones to attempt something like this, but nowadays this is sort of, there are lots and lots of papers that come up with also very creative new methods for performing this equation of state inference and using the PQCD bound as an extra constraint as well. The one reason for this activity is that this is a rapidly developing field also in terms of observations. NOISR will be replaced by new X-ray observatories, XP and EXTP in the coming years. LIGO, Virgo, and CAGRA are all the time, this should have been K by the way, not G, are producing new gravitational wave results all the time, and they will be complemented by the Einstein telescope and the Cosmic Explorer in the next 10 years or so, which will really revolutionize this gravitational wave interferometry field, and we will basically have thousands of more binary neutron star gravitational wave observations in about 10 years from now, and hopefully also a clean measurement of the post-merger signal. And finally, there is very rapid progress at low densities in chiral effective field theory calculations that I have completely skipped here. That's not my field, but certainly there are lots of efforts to bring this, similarly to what we are doing, trying to bring this PQCD, kind of improve the accuracy of this PQCD bound and bring it to lower densities. There are sort of major efforts to improve this chiral effective theory computations at low density and bring their regime of validity from the current 1.1, 1.2 saturation densities to close to 2 saturation densities. But like I mentioned already, there's this new tool called thermal loop tree duality that for the first time has made it realistic and very much viable to complete this N3LO pressure of cold and dense quark matter in perturbation theory, and I dare claim that very soon, in a matter of months, we will be releasing a paper where this PQCD band here is replaced by something considerably more constraining, this meaning this N3LO band here. Thank you. Any questions?
Concerning one of the last points, so approaching the high density limit below, so starting from chiral effective fields, I read that there are studies by Weiss and his collaborators considering the fact that the nucleon is a core which is quite compact, surrounded by a cloud, so that even if you go to high density, this is not enough to make the cores overlap. So they tend to support the idea that there is not a first order phase transition, and they try to attempt similar analysis. I mean, what do you think about this complementary approach?
So I mean, I'm aware of these works. I think they're very interesting. This is, I'm not a nuclear theorist. My I don't know, my understanding is that they are sort of their results have been challenged by the more kind of traditional chiral effective field theory practitioners, and but it's certainly very kind of very interesting that there is an approach that really seems to. I think his claim is even that you can go all the way up to something like 8 saturation density, still being the nuclear matter phase, and that he has a methodology to do kind of robustly use nuclear degrees of freedom all the way to those kinds of densities. So I mean, my personal take here is just that I this is not my specialty. This is not something where I'm qualified to really say much, but I would be generally kind of surprised and very impressed if that turned out to be the case. One I mean, from the point of view of our PQCD calculations, I don't think that we will ever be able to see really traces of phase transition. So what we will be able to do is maybe bring the current matching point where we kind of stop using the PQCD results is about 40 saturation densities. In a very optimistic scenario, we will be able to bring that down to 20 saturation densities. But that still, of course, leaves quite a lot of room for Wolfram's claim to be true. Like there's still kind of, it might be that the change in the degrees of freedom would happen between 8 and 20 saturation densities, but I mean, naively speaking, that would sound very surprising. But who knows? I mean, I really don't want to take a very strong stance on this.
There are several efforts to try to constrain the region that the experimental data structure and
Yep. Yes. Yes. Yeah, absolutely. So I due to the lack of time, I completely skipped this low density part, but it's certainly true. I mean, the way that this whole, I mean, the chiral effective field theory is an effective field theory that then contains parameters that need to be matched to experiments, and then they of course use nucleon scattering measurements very heavily to constrain the values of their, or to improve their predictions. What comes to heavy ion data, this is extremely interesting, and this is something that I think will in the future will be used a lot, especially when one wants to exit the zero temperature regime. So this is something that we will be working on a lot in the coming years, generalizing both our perturbative calculations and our interpolation calculations to non-zero temperatures, and there I think that heavy ion data will play a crucial role, because there, of course, once it's the whole phase diagram rather than just the zero temperature mu b axis that where one needs to do some kind of an interpolation. So there I think that heavy ion data will be constraining. Of course they have been used already to constrain the zero temperature equation of state, but I think that so far the effects haven't been very large, but in the future I believe they will improve a lot.
The second point we suggested is that the hydrons might from the diffusion state. And first, does the rise of hydrons in agreement with the experimental data?
Yeah, I mean that was sort of just kind of qualitatively, yeah, that's one of the questions that one could, in principle, ask whether this apparent softening would be due to hyperons, and this is something that we studied very carefully. So we went through basically every single nuclear or hadronic equation of state in the composed database and compared their predictions to what we get. And in the end, I mean, it's true that hyperonic equations of states often introduce a softening in the equation of state, but there's not a single model that would actually be consistent with all the observational constraints that we are using. So we kind of, especially in this Bayesian calculation that I explained here, we kind of did try to evaluate all available hadronic equations of state and give them a kind of a likelihood value, and none of them did very well. So there's, like, qualitatively you can get a similar effect of the system becoming more conformal, but in those models where that happens, they then fail in some other respect. So I mean, maybe hyperons play some kind of a role in here, but I doubt that this qualitative change that we observe in the equation state around here is just due to hyperons.
You have not mentioned the conductivity.
Oh yeah, that's a very interesting direction to go to. So from the point of view of our perturbative calculations, let me just go all the way here. From the point of view of our perturbative calculations, that's not so far, that hasn't been very important, and the reason is simply that the contribution from quark pairing to the equation of state, it scales like the gap squared times the baryon chemical potential squared, while this kind of the contribution we are computing scales like mu b to the fourth, and this means that the pairing contributions are very strongly suppressed by something like delta squared over mu b squared, where delta is about 50 or 100 MeV at high densities, and basically all the way down to these densities that we have here, I don't know, 2.6 GeV for the baryon chemical potential, you would get a sub 1% effect at best from quark pairing. But then if our N3LO calculation behaves as well as we hope, then it might be that one has to start considering, then it might be that one would, instead of a kind of 1 per mil, one would get a 2%, 5% effect from there, and then of course that should be taken into account. But of course then the issue is that the pairing gap is something that one really needs to treat as a free parameter, because nobody can really compute that. But I would say here it's sort of it might have an impact, but not a very large one. Then when it comes to more dynamic questions, transport, for instance, in the transport properties of nuclear matter and quark matter, in merger dynamics, their pairing can be very important. So there one indeed might get qualitatively different results if one takes pairing into account. And this is, that's a long discussion, but yeah, there's a lot of work to be done in that end.